Ja. Ah, okay. Okay, das gibt ich habe gestern, nachdem wir gesprochen haben, dann noch ein bisschen was nachgedacht. Aber jetzt ist das so viel.
For a moment. I don't really need this. Maybe that's the microphone. So put it here. Thank you very much.
Ja. Ja.
A minor detail. You're not sharing a screen yet.
Oh, yeah.
So sharing without. So let me check.
Ja. Ja, genau, ja. Ja. Ja.
Do they start 10 minutes late here in Greece? 15? Or on time? Pardon me? Couple minutes? Steep angle.
Sorry?
Can you read anything from there?
Yeah. No, I've been here the whole time. All the other talks.
Yeah. Just because you're all the way from Australia, right? Yeah, where everything is at a distance. Takes a long time. Yeah.
So, it is with enormous pleasure to introduce to you Dan Anderson, who came to us all the way from Kenya. No. Sorry, was unfair. All the way from Boulder to talk about something that I find very exciting. Because I started this conference with matter wave optics, right? But the equivalence between matter waves and optical waves is something that few people appreciate fully, and it's a very fascinating. So the equations, as you will see, resemble each other tremendously. And there are some great subtleties which I'm looking forward to learning about, because I still understand only half of it. So,
Thank you, Wolf. It's a pleasure to be here. It's a great pleasure for me to be providing a couple of lectures at the summer school. The best thing that you can do is to feel comfortable asking me questions. In my view, this stuff is both obvious, but then in fact, very subtle. And so whether it's seemingly an elementary question or seemingly way out, in left field, I'd be happy to hear you ask the questions. So please, again, I'll hope you feel comfortable.
It's not a question. Can you just
What'd you say? There's this 1 over r squared fall off. Yeah, what'd you say? There are also seats here, so let me. What? Yeah. I encourage you to come closer. Yes. Okay. I'll tell you what. I'll speak from here. Okay. Yes.
Dana raised a very but trivial question. Students are often afraid to ask trivial questions. Surely everybody knows the answer. Actually, it's the opposite. If you have a question, probably we forgot to say something. And probably the person next to you, there are 20 people in the room also. And you'll be the hero who asks.
Yes, please ask.
And if you do that twice, he's going to know you, which raises your salary by at least 20%.
Okay, so I'll also walk up here often, since that's where the wind is, and I can tell that right here is the hottest place in the room. All right, so in these lectures, I'm going to introduce a class of matter waves that most, if not all of you, are not familiar with. They're based on a set of matter wave duals to Maxwell's equations. How do I change the volume? Tell me to talk louder. Based on matter wave duals to Maxwell's equations describing electromagnetics. And what I'm going to talk about today is I'll introduce the gauge field theory leading to these Maxwell equation duals. Now, I know there's at least one. How many of you are theorists? I know I met a couple at lunch, so I know. And how many of you are experimentalists? Okay, so these guys will like to lecture today and you'll like the lecture tomorrow. Today's the gauge field theory leading to Maxwell's equations, the Maxwell equation duals. And tomorrow I'll talk about properties of these Maxwell matter waves. And that, for the experimentalists especially, will be useful and interesting. But what I want to say is somehow the word artificial came into my talk title. There is nothing artificial about the gauge fields, meaning synthetic. These gauge fields describe very natural phenomena. It's merely used as theory to lead us to these Maxwell equation duals. And I also want to say that the solutions to these duals to Maxwell's equation are a legitimate full description of a phenomena, of a physical phenomena, as much as solutions to Schrodinger's equation are meaningful physical descriptions of the laws of nature. And the surprising thing to me, really, in retrospect, is that these weren't recognized much earlier than today. We were doing other things, I suspect. So let's go back and start with quantum. And we can say that it was born in 1900 by Max Planck, who said light is emitted in packets of energy. Now we call it photon. This should be familiar. And then de Broglie, 100 years ago, came along and said, well, massive particles must have wave-like properties. This he deduced because light, which was known and recognized as a wave, evidently, according to Planck, had particle-like properties. Therefore, the reverse ought to be true. All right? And this wave-particle duality is uniquely quantum mechanical phenomenon. And we know there's superposition, there's tunneling, there's quantum entanglement. That gets exciting. I'm not going to talk about that. But those are very much quantum mechanical characteristics, and the substantial evidence that matter has wave-like properties was the early diffraction experiments of folks like Davis and Germer. All right, let me give you some motivations for what's missing in our matter wave world that we're very familiar with in optics. What is it that's missing? I'm going to point to the absence of temporal coherence. And those of you who know me, which is essentially zero here except for Wolf, know I'm an experimentalist. I like to show whack factor. What do I care? What measurement does this impact? And so let me point to that in two steps. One is, you're already familiar with it. You've heard it at this meeting. You'll hear more of it at this meeting, in fact, after my talk. It's the exploitation of de Broglie. And I'm going to be referring to de Broglie matter waves, and then Maxwell matter waves is what we're learning about today. So we know that we can use an atom beam, typically cold, often very cold, to make very precise, sensitive measurements, say, of forces. So you can take an atom beam. And by the way, I'm colorblind, so this is the first time you get to see, I think, a blue laser pointer. I don't see the red dot, but I can see the green dot. An atom beam is split into two. By a light field, and those two pieces of the atoms are then exchanged or reflected with another light field, and this is time along this axis, and then you recombine it to get out a signal by measuring the relative populations in these two beams. For example, tells you the acceleration in the direction of this line here. So we see that's exquisitely sensitive. A lot of us spend a lot of time trying to make this work really well. A lot of you do, I'm aware. So you're familiar. Bragg or Raman light pulses are used to split, reflect, and then recombine atom beams. Now here's the so what. This is not what we typically do in optics. In optics, for example, LIGO, the gravitational wave detector, what do we do to make a better detector? We typically put the light inside of a resonator, and we use resonant effects of some resonator to increase our sensitivity or to build up light. For example, in ring down cavity spectrometry, if you've heard of that. Resonators are very powerful ways of increasing signal or making something work better because light bounces many times between two or more mirrors. So until now, all the atom interferometry you've ever seen follows this rule: split, reflect, recombine, done. Now there's some fancy things done with it. You might have heard from Kerry Widener and so on, but it's still a matter of putting atoms, splitting them, recombining them, make a measurement. We have not seen resonant matter wave interferometers, and the reason is because there have been no sources of coherent matter wave sources. Sorry for the double use of sources. And here, I mean coherent with a capital C, meaning Glauber coherence, and particular, I mean temporal coherence, classical temporal coherence. Yes. What is global coherence? I hope will become clearer later, but for now, I'll say is you make a measurement of something typically as a function of time over here, and over here, which is either later or in space, it somehow evolves at the same rate, and you have a very well-defined phase between what's happening here and what's happening here. Does that make sense?
I just call it coherence. What makes it global?
What makes it global? The fact that it's not local. And I don't mean to be, so what I mean is there is a clock involved, and there's something that goes tick that's independent of where you measure it. And if you keep that question in mind, it's an excellent question, actually. You can ask it again in a few slides or see if it helps in a few slides for now. Okay? Thank you for asking the question. All right. If I did, yes.
We're starting to see some like continuous matter waves, like kind of laser.
Yes.
Would that be current in this regard?
It is. So the BEC, first of all, in general, is quantum mechanically coherent. It is not a temporally coherent source of atoms. You make it into a continuous. It is also not temporally coherent. It is quantum mechanically coherent. Yes. And I specifically am going to be teaching you today about the temporal coherence and why that's significant. All right, did I answer your question? Yeah. So it's still coherent, but not temporally coherent. All right. Suppose I did have some temporally coherent matter wave source. Then I could do something. I haven't taught you how to do this yet. But if I did, I'd have some sort of oscillator, the equivalent of a laser, put out a matter wave, and then I could reflect, between two matter wave reflectors, and they're incredibly easy to make. I intentionally made these blue because if you detune a laser beam to the blue of some atomic resonance, you can make a reflector. That's not the topic of today's talk, but this is conceptually easy to do. And then I could have a resonator, and I can have an arrangement very similar to what's done in optics, measuring the resonant frequency and feeding back the oscillator to maintain resonance. Don't worry if you don't understand this. Just to say that I can do something that's very similar to what's done in optics. And if I make two of these things, for example, I could make an accelerometer. So I have one aligned along some acceleration or along a gravitational field, another which is perpendicular to it. And here's the key, that instead of a phase, you can measure the frequency shift because the matter wave that goes here has to climb up against the gravitational potential and then fall. This one stays in a constant gravitational potential. This frequency, resonant frequency, will actually go down or at any rate change, by an amount that depends on the acceleration and the sensitivity of this device. You don't need to know the details. The key is the sensitivity has this factor of F, which is the cavity finesse. And it's in the bottom here. So you have the finesse, which means how many times effectively does the matter wave bounce between these two reflectors before you lose it. And you'd like that number to be high. And if that number is high, you can measure very small changes or measure gravity, for example, to very good precision. So given a size of some system, if you can make a resonator instead of a single pass device, you can make it much more sensitive. But to do this, in fact, this has to be a temporally coherent source of matter waves. So let's talk about that. Waves having temporal coherence. And this, yes.
Yes. What's experimentally our optics? Is there pulses or it's...
Good question. These can be, in fact, CW laser beams that are shaped. It might be Gaussian in this direction, all right, or Gaussian this way, but shaped like a knife, so long, and that will turn out to be a good reflector of matter waves. If you detune this laser light to the blue of atomic resonance, it acts like a mirror, because the atoms will be repelled from light which is detuned to the blue side of their resonance. Continuous. Yes. Okay. It would be very similar to what's in optics. It's how long, the longer that you can have the atoms and the matter wave inside between those two reflectors, the better. And so you need, if you want to do something interesting, you'd like, and very precise, you'd like a very long coherence time. And then you would set the reflectivities of those mirrors to correspondingly make maximum use of this coherence time. Wouldn't we love a second or more of coherence? Or I think Holger Müller and others have shown really long coherence times of atoms. Those aren't matter waves, but of atoms. So you'd like really long coherence time if you want precise measurements. All right, here's the original lesson, truly the original lesson in temporal coherence. And it's in light. And we know it from James Clerk Maxwell. And Maxwell unified the theories behind electric and magnetic forces, recognizing as two manifestations of a single electromagnetic phenomena also identified with light. And here are some equations which I suspect are familiar. There's Gauss's law. There's Gauss's law for magnetism, Faraday's law of induction, and there's Ampere's law plus Maxwell's entrance of the displacement current. So these may not be your favorite equations, but you've seen them. All right, they're very familiar. And two dynamical parameters go along with these equations. One is the speed of light. That's implicit in this mu naught epsilon naught. And the other one, which for some reason physicists don't talk about that much, is the impedance of free space, which is 377 ohms. All right? These together with mu naught and epsilon naught, or these together with the speed of light and the impedance of free space equivalently, determine everything about the electromagnetic world, until you bring in other matter and stuff, but this is at least in vacuum. And you know well that the speed of light is an upper speed limit. We don't know how to get something to go from lower than the speed of light to above the speed of light. Okay, what did we learn from Maxwell? Well, we learned that if we have a current that varies in particular in time, it'll give rise to these fields, E and B, the electromagnetic fields. That the information propagates at speed c, and there's the impedance of free space. We also learned that, for example, if we arrange things right, that if we have a wire, for example, and get current to move up and down, that this wire will generate an electromagnetic field All right, an oscillating current will give rise to a radiated, classically and quantum mechanically coherent electromagnetic field. The amazing thing is that a classical current gives rise to a quantum mechanical approximate, quantum mechanical pure state. All right, and this is the original lesson in temporal coherence and the connection between a current and a radiated field. You also may be familiar with the quantizations, and this isn't, meant to be a heavy quantum lecture or anything like that, but just to remind ourselves, what is the connection between the classical field and the quantum mechanical coherence? Well, there's a nice dual or analog between the electromagnetic field and the harmonic oscillator. And you know, a harmonic oscillator has discrete levels which are equally spaced, given by the spacing of the harmonic oscillator frequency times h bar. And then I can have these. I would say if you're taking notes, don't take notes on this part. This is a reminder. It's not the meat of what I'm trying to say, but it'll be useful as a backdrop. So we introduce these creation and annihilation operators, and we can apply a raising operator, which raises the state of the system by one dot on the energy level, and the annihilation operator, which lowers the state, an eigenstate of the system from being one level to one lower down. In the coherent state, once I introduce these operators and their properties with the level number, well, I can introduce the Hamiltonian, and it was Roy Glauber who introduced what is the classically and quantum mechanically coherent state. It is a state of the system, in our case of a field, which is an eigenstate of the annihilation operator. And that's what we mean when we say, well, this classical coherence also has quantum mechanical coherence. And a radio transmitter, as well as a laser, produce an approximation to a coherent state. But here's the takeaway. From Maxwell's equations, a classical current generates a quantum mechanically coherent state. Okay. So Maxwell, we know, or we're always told, that Maxwell came up with his equations by looking at the separate empirical phenomena of the greats before him, such as Ampere, and assembled them into electromagnetics, into Maxwell's equation and the wave equation. But in the last century, apart from quantum mechanics, another very significant revelation was that even Maxwell's equations themselves can be derived from gauge field theory. You don't need, to have observed electromagnetic phenomenon, individually at least, to come up with Maxwell's equations. And in fact, this gauge theory was ultimately led to the unification of the electromagnetic and weak forces to make the electroweak forces, and also used to come up with the strong force. And it's been tried so far unsuccessfully to sort of integrate gravity into it. So my point here, the take-home message of that slide is Maxwell's equations fall out of the application of gauge field theory. And how many of you know what gauge field theory is? Anybody on this side? You're embarrassed to raise your hand. Be proud. Okay, 2 here. 2.5. Okay. Well, so one thing I tell you is I stayed away from gauge theory until I was old. And then I felt I had no choice and I had to go learn it. And then I discovered something very interesting was learning it was especially difficult for the context I'm about to describe to you, because it was so customary how it was done, and it was only done basically in one context. It was all the more difficult to apply to something entirely new. All right, so here's a quiz. Consider now a time-dependent current, say, of neutral atoms, such as rubidium-87. All right, so it's red instead of what other color I had before. Here's a current of neutral atoms. Is there a set of fields associated with that current? set of atoms, neutral atoms. Well, here's a hint. We know that electrons repel each other, right? Well, as it happens, so does neutral rubidium-87. Moves a little slower, maybe, but they'll scatter off each other. They'll, if they're going cold enough, they'll simply bounce off each other in a very simple way. So electrons are identical particles and repel each other. And they repel each other through Coulomb interactions. They exchange photons. Ultra-cold rubidium atoms also repel each other through van der Waals interactions. We don't usually talk about what they exchange. We know that van der Waals forces are ultimately electromagnetic. So a side comment is, there is no new physics being introduced here. No new physics. Van der Waals is actually electromagnetics, not talking about new forces or something like that. We're just noting that they are identical, rubidium-87 atoms. They repel, and what do they exchange? I'm not sure. But the answer to the question is, does a current of neutral atoms, an oscillating current in particular, generate fields? The answer is yes. A set of gauge fields is associated with any interacting identical particles, period. Any interact, they could be bananas if they're interacting. All right, well, okay, it's hard to quantize bananas. All right. The van der Waals interactions of multiple atoms are ultra electromagnetic, but field theory doesn't actually care what is the origin of the interactions. No more than quantum mechanics really cares that much about the nature of a particle you have, not in great detail, other than things that affect its quantum mechanical properties. But if you have one neutral mass and another neutral mass, quantum mechanics says pretty much the same things about them. So the gauge theory that we apply here doesn't care what the origin of the interactions are, just that there are interactions. And on various symmetries, and this is all about, the fact that in the end, electromagnetics involves electrons, which, for example, have spin. Other particles in the universe have a bit of character. So this statement is not that useful to us at the moment. Ultra-cold rubidium atoms move terribly slowly, and their interaction is actually very simple. It's called S-wave scattering. They look like ping pong balls bouncing off each other. And when I talk about oscillation frequencies here, temporal coherence, I'm talking about frequencies about 1 kilohertz is a pretty big one. We're not talking gigahertz. We're not talking optical frequencies. We're talking about big, heavy things moving this fast. That's actually a reasonable amount of energy. Yes. Say again?
What is the meaning of
we are about to find out the meaning very shortly, so either reserve that question and ask it again, or nod your head and say, okay, I got it, okay? That's exactly what we're talking about. Yes?
So if I understand correctly, you say, all right, experimentally or from other theories, we know that neutral atoms between each other will interact.
Yes.
And then from this you build an effective field theory.
Yes.
And then in this theory, fields will
yes. And I'd love to know why, from you, since you're a theorist, why you'd call it effective. When we write down Schrodinger's equation, we don't say it's an effective anything theory. We apply the rules of quantum mechanics, but it doesn't really matter. I'm just curious. I've heard the theories before, an effective gauge theory.
Because we know that it's actually electromagnetic field theory, right?
Yeah, but who cares?
It's pretty deep, but...
So this is it, yeah. I mean, you're right. And theorists often say you'd have an effective one, but I don't worry about effective when I talk about quantum mechanics. For example, I don't talk about, say, what is the source of my energy field that's constraining atoms? You're right in your language, it's effective. I just don't know why anybody bothers with the word. But yes, it's an effective field theory. So the reason why I found this very difficult is because all modern treatments of field theory incorporate relativity very early on. But I don't care about relativity. I've got very small slow-moving atoms. And if you want to really learn about this stuff without it being applied to in particle physics or bringing relatively early, it's the people who worried about this thing early on who captured it. So these are notes of Nicholas Wheeler of Reed College, written about 1981. And, you know, as I say, all modern textbooks pretty much introduce relativity early on. We're not going to introduce relativity at all. The process of applying gauge field theory is always the same. And so we just pretty much followed his development. So in some sense, you know, we just copied somebody else, but applied it to neutral atoms. And this is well before neutral atoms got really, really cold, where this stuff makes sense to do. So classical field theory, and you can, anybody can correct me if they'd like, is done in 6, quote, easy steps. First, start with the Lagrangian for reflexive particles, and this is what it is. You don't have to memorize this, especially the experimentalists. It's not important. Eventually we'll have Maxwell's equations and we won't care about this. But this is the way you start all new physics, is by writing it down the Lagrangian. And if it's quantum, you often start with the Hamiltonian instead. All right? And this Lagrangian has a particle density in it on the outside, and it has inside of it Hamilton's principal function. All right? And then you identify global gauge invariance. For example, you know that if I drop a ball from this height, the way it gets down to the floor is the same, or whether I call this zero potential energy, or if I call it plus mgh potential energy. All right, so there's an invariance there. And then after I identify global gauge invariance, like this energy constant, I introduce gauge fields, a vector gauge field and a scalar gauge field, to introduce what's called local gauge invariance. And then, so these are now fields which you use to impose local gauge invariance. And then you add the interaction between these fields and the particles to the Lagrangian. And then finally, you add the energy in these fields in the first place to the Lagrangian. And then we use Hamilton-Jacobi equations to find all fields and conditions. All right. Now, back to your question. What do you mean by global coherence? Remember that question? Okay. So I'm going to introduce the gauge field theory of superballs, or rubber balls. All right, imagine I have a collection of rubber balls, all identical, and I have on the left-hand wall a vibrating arm, which is vibrating at frequency nu. All right? Now, because these balls interact, because they're rubber, all right, I can get some of these balls to fall off the edge of this little cliff here, and then go along this potential surface, and then, for example, raise back up. The fact that these balls are being vibrated at frequency nu is global. All right, that somehow there's a record of that vibration carried by these balls, and even when they're far apart, not touching, therefore not interacting, right? They know, or the system knows, that they've been vibrated in such a way that they roll back up, that pretty much they'll be touching each other again, and the same thing will be going on as the left on the right. That's what global coherence means. Because this frequency, no matter where we are here, it's recorded in the way that these balls have interacted from here on. And so that's what we mean by temporal coherence. That's what we mean by global coherence. Does that kind of get at what you're asking about? Maybe. Okay, I hope so. All right.
I have a question. What would be the absence of global coherence in this picture? But I guess it's possible to also.
What's the absence? If there is no frequency associated with it, so somehow I just, you know, I'm not sure this is such a good example, but if I push them off, there would be no way I could measure over here what was going on over here. All right, so there's something about a clock somewhere in the system that has been embedded into the particles and the way they've interacted. The other thing to note, by the way, another note is that van der Waals forces, like these rubber balls, are near field. Only, they're short range. One more thing that this picture does not depict is in quantum mechanics, if I have a particle and its wave function, it's a plane wave, right? The wave function, if they're in vacuum and they're in an energy eigenstate, then they're not localized. The wave functions are also extended. And therefore, near field interactions or short distance interactions has no real meaning, right? Because the things are all global, but they're still interacting. There's still an interaction energy between them, even though they're not localized. So for those of you who get stuck on the notion that van der Waals are short range, remember when I go into quantum mechanics, particles are extended. All right. So if you want to read more about applying gauge field theory to neutral atoms, it's here, and this lecture is being recorded, so you can go back and look at the lecture to capture. This is where I and my colleague Kasia put this down on paper. All right. So this is the story that any set of interacting particles, identical particles, will have associated with them a set of equations, if they're simple, like S-wave scattering, that are Maxwell-like. And so you can think of classical field theory. If we go through classical field theory and we apply relativity, we get Maxwell's equations. All right, so the general theory is constrained by the empirical laws we've already determined out from the speed of light and the impedance of free space that defines everything. On the other hand, if you forego relativity, don't stick it in there, but instead say that quantum mechanics is our reality instead of relativity. And we're very worried about relativity. Remember, these atoms are moving very slowly. Then you get another set of Maxwell's equations. I've chosen different symbols here, just so not to be too confusing, F and G instead of E and B. But you get an identical set of Maxwell's equations constrained by the laws of quantum mechanics instead of relativity. So in the usual electromagnetics, the particle electrons, in our matter waves, they are atoms. They could be neutrons, they could be et cetera, but I'm interested in atoms. The gauge field, well, it's the electromagnetic waves, the E and B fields that you're familiar with. That is the gauge field. In our case, for lack of a better term, we call them matter waves instead of electromagnetic waves. Maxwell's equations that we know are constrained by the empirical speed of light and impedance. And instead, in matter waves, they're constrained by a particle group velocity, and in fact, the quantum impedance, which is h bar. And, well, you didn't think of h bar as an impedance before, but it has exactly the right units. It's if you measure things in terms of energy per particle per second, for example, that is an impedance.
It starts off with a Lagrange, and you say you wanted to be invariant under Lorentz transformations, like loop.
Right.
You end up with those equations. On the right of quantum mechanics, does that mean you wanted to be invariant under Galilean transformations?
I would say your first statement is true today, but not what you would have said when you're first doing them. You want to be not invariant under, what did you say? Under Lorentz transformations. That's not how you get them in the first place. You said you would get those set of Maxwell's equations asking for local invariance, nothing to do with relativity at all. But they travel at the speed of light and they have this impedance. Then it just happens, they happen also to obey relativity, and they're special that way. Yes.
So for no interactions, you exchange the photons, and you left it as an emission for van der Waals interactions. What's exchanged?
Good. What is exchange? So the point of the question is, for every gauge field, like in electromagnetics, you have a gauge boson, which we name the photon. So I'm going to have a gauge particle also here. And if I had to name it, which I did, we call it the matteron. It's a terrible name. And it's actually not that useful. The photon actually sort of got its own identity and becomes very useful to think. You'll see why in a moment. Although I name it a matteron, as I said, it doesn't play quite the independent role that the photon does in electromagnetics. Yes.
Fundamental interactions are similar to electromagnetic. Is the matteron?
Yeah, matteron.
Have the same properties?
No, absolutely not. And you'll see that's what's so interesting. Yep.
Regarding the last, I understand that you and
Yep.
When you do the treatment of the onion, you can get like a chemical type equation.
Yes, you can. Right. It gives that velocity, but yes. So de Broglie waves propagate at the, phase velocity or group velocity is what you say the particle after. That's correct, but there's no temporal coherence. So we'll see how they get married in a moment.
I don't see where the gauge is only because
Yes, you assume they interact. So that's why the gauge field theory is there. And I'm hoping that this will become that the answer to your question also becomes more apparent as we go along. Yes.
One wave, and in particle we have wave particle, and the temporal coherence is for the total wave particle.
As opposed to the individual ones? Yes, in some respects, in the same way that you might say that the electromagnetic field is many body or many particles, many photons. In the same way, you would say so here as well. It's a coherent state of the atoms. Again, I think this will crystallize a bit better for you just shortly in the moment. But so either hold the question, answer it again, or it'll be answered.
I'm thinking about Maxwell equation before the Maxwell equation before the.
Go ahead.
So now we are
Yes. You mean you don't have to talk about photons when you do the electromagnetic field? That's absolutely true. All right. So this is some field, and in about within a couple of slides, you'll get a very significant thing. And I'm going to, given the time, I love the questions, but given the time, I already did that slide. This walks through how you actually apply gauge field theory. I hope it's okay if I skip over this. It's very standard because I want to get to some of the answers to these questions. This just walks through the formal process of introducing the gauge potentials, A and phi, and then how you get the fields from there. And we can go back over this, but given how time is hopping along, I think I'll get to things that should get your questions. So again, here are Maxwell's equations. And what's key is, in the gauge field theory, is that they're tied by the empirical facts of the speed of light and the impedance of free space. And by the way, you can also cast things directly in terms of potentials and get the fields from those potentials. We can do all those same things here. And now, okay. Instead of bringing relativity in the speed of light, we incorporate quantum mechanics utilizing the group velocity of the particles. I've said this already, but this is now more explicit. The key about the group velocity is that it is dependent on the frequency of the particles that you're working with. All right, so, and in particular, this is a velocity, so it looks like a nu, but that's a v, tech v. And instead of the speed of light, you get a group velocity, and that's dispersive. It depends on the energy of the particles in the first place. And then there's a wave vector associated with the electromagnetic wave. Here, there is a wave vector associated with the equivalent Maxwell matter wave gauge field, which the K vector is given by this frequency of oscillation that I'm going to now refer to, the vibrating frequency against the wall, divided by this velocity. This is not the de Broglie wave vector. This is a new matter wave vector, given by, again, the ratio of the frequency of oscillation divided by this group velocity at that vibration, corresponding to energy associated with that vibration frequency. And there's a quantum mechanical impedance, which I said is h bar, or if you like different units, you divide by m squared. So if you like to talk about masses and particles, particle fluxes in terms of mass, you have this impedance. Or if you just want to measure particles as, particles per second and so on, then it's just the h bar is the impedance. And you can define a potential in the same way that you do in electronics and electromagnetics when you talk about a wave propagating down either a waveguide or down a wire, for example. We don't have wires, but it'll be convenient to have an electronic analog. And here's, not many of you, if you're not from the US, you won't get this. This is a turkey before Thanksgiving, looking at the predicted temperature for the next day, which is 350 degrees Fahrenheit. And it says this can't be right. There are going to be some conclusions from this theory which are going to be surprising. You're going to say, that can't be right. Okay? They're going to bug you, I promise. So here are the non-trivial and unintuitive changes from Maxwell's equation. Change number one, the speed limit is not a maximum, it's a minimum. And actually, it's not even really formally a minimum, it's just a limiting velocity in a very formal sense, or you might call it, I don't like using the word critical, it's not a critical velocity, but it is a special velocity, and is not a maximum, it's closer to a minimum. It's dispersive. The velocity that we have that replaces the speed of light depends on the oscillation frequency that we're talking about. Why minimum? There's a nice physical answer, but I'm going to leave it for now. And there are no source-free fields. The photon has an identity all itself. You have a photon over here. You've forgotten the fact that it took an electron or something somewhere to generate that photon. It has a life of its own. It turns out that there are no source-free fields. There are only fields when there are also sources. There are only the gauge fields when there are also the atoms around. And the interesting thing is that there's a physical reason for it. And again, it's very non-intuitive at first. Then we can define an index of refraction, which is the ratio of the actual velocity of the particles to this sort of limiting velocity. And that's given also by the ratio of the frequency of oscillation that you're interested in divided by the Planck-Einstein frequency omega. All right, so there's an index of refraction. We in optics love that. It's just a ratio of the actual velocity to a limiting velocity. And that turns out to be very useful. And there's some more non-intuitive changes compared to what you're used to. One is there's a characteristic impedance, has H bar. it has this index of refraction in the bottom of it, but the point is it has a minus sign in front of it. The impedance associated with the matter wave is negative, and that turns out to be why there are no source-free fields. The equivalent of the photon is bound to its particle, not free to radiate. It is bound to it. Nevertheless, it's still real and it's still there. In microwave terminology, and it's very nice to use circuit analogies for these matter waves for a variety of reasons, this is called the characteristic impedance. So you can write a current in terms of, a voltage in terms of a current times an impedance. And this voltage is not in coulombs, it's in energy per particle, or energy per kilogram, if you like. And the current is not, coulombs per second, it's kilogram per second or particles per second. And this negative impedance means the power carried by the field, the wave, is negative. And that has some fascinating consequences. It doesn't contradict anything, it turns out, but it has its own consequences that you're not used to. And among other things, that means if you have a circuit, which is a matter wave circuit, or you don't have to think of circuits, you can think of waveguides and so on. The point is, if you have a source, sources are usually ascribed an internal resistance or something that makes them non-ideal. And the emission of a matter wave will cause this internal resistance or source resistance to cool instead of heat up. Normally current, the current flowing out of battery causes the battery to heat up, or your flashlight to heat up, or whatever. This will actually cause it to cool, which again has very important consequences from a utility point of view. Yes?
When you speak about wave and source, is it like the wave that is emitted by your source? Or
yeah, so the point is, there is no emission here. There's a field, all right? And now there's a field associated with the particles. So we call the particles the source. There's a field associated with them, but there's no radiation. They are bound together, all right? And it does get confusing because we say matter wave, you say, what do you mean? Do you mean the field? Do you mean the atoms? Or do you mean some combination? You'd have to ask me, but generally I mean together, the atoms and the gauge field form one overall matter wave because they're stuck together. All right, it's very discomforting to say, well, this field is stuck to the atoms, so what good is it? But it's real, and you'll see, well, maybe you won't see why, and I'll finish it tomorrow. Say again? Yes, it's a very good question, and I can tell you this. For one thing, I had that question in mind that somebody would ask, and my answer was, I don't have a great intuition to explain it, but I'll say this. It is due in part because, as I told you, the speed is a minimum, not a maximum, and generally particles are going faster than their minimum, and that's directly connected with this minus sign, as it turns out. But is that intuitive? Not really, but it is why you get a negative sign. Yes. Yes, so if you like that intuitive explanation, I'm delighted. Okay. I think that since we're already at almost time and I want to ask more questions, the rest of this I can cover in my lecture tomorrow, where you learn about the properties of these matter waves. So the key is these matter waves are parameterized by two things. Normally, we just have the mass of an atom and its energy. That's it in quantum mechanics. And let's forget about the mass. The Hamiltonian just has, h bar omega basically is the energy. Here there are always two parameters. There's the energy of the particle, but there's also the frequency in which I'm modulating something. You'll learn better when I'm modulating later, but when we create a particle plus its gauge field, we have to have two numbers for a single mode. In electromagnetics, a single mode is defined by only the frequency of the oscillation. In quantum mechanics and mass, we're usually giving only one number, which is the Planck-Einstein frequency or energy of that particle. Now we've got both. And so there are two parameters, the energy of the particle and the frequency with which I'm oscillating that is associated with the field. So those two parameters, and that makes life a bit different. And so we're going to talk about how these waves reflect off of a step boundary, how the harmonic oscillator modes associated with these waves, the waves associated with the Fabry-Perot, all of them are rather different than what you're used to, either in optics or in matter waves. So I think I'll stop and take remaining, questions in the 3 minutes. Unfortunately, we have an hour and a half? Oh, great. I got it. What? Okay. I have half an hour, one more half an hour. Yeah, good. Good. Go ahead. Yes.
Explain the whole global sense of things. And in the field theory, I think it's a gauge invariant. But
Yeah.
how come if it's a gauge invariant that we have finite coherence times?
Finite coherence times. Let me make sure I understand. So in coherence time, for example, a laser has a coherence width because it's not a perfect laser. Is that what you mean? Good question. So in the end, all of this stuff we're doing is a closed system. There is no decoherence. All right. If I want to start, what?
Everything's conserved.
Everything's conserved. If I want to open up the world, I can do that, but I've got more work to do. Okay? Yeah. 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 So what she asked, if you have true gauge invariance, which is supposed to be global, what about decoherence? And my statement is everything I'm talking about now is in a closed world. Everything's conserved. So it's not an open quantum system. There is no decoherence. I have extra work to do is to make an open quantum system, which we can do, but it's not yet part of a lecture. Yes. I'll repeat it every time. Okay. Could you say, I can't hear you very well. Yes. Exactly right. That's right. So power is carried by the field, right? So the power in this case, we go from left to right. It's positive power, and it heats up the resistor. Here, if you like, the power is going right to left. It's negative, right? So if you want. So it ends up cooling. It's working everything backwards. The other thing I want to say is the reason that everything's okay, though, is I'm only talking about the contribution of the field. The field also has with it the matter, all right? And the matter always has positive energy. So net, you always have positive energy flow. Things always heat up. Just the field alone, though, causes cooling. So that's very important to not get comfortable with negative energies. Is one always, in the ends, have positive energy. One always has positive power flowing. But the field itself cools. And that, yeah. Radiative cooling actually is an open system, and this is closed. And so, he asked, is it the same as radiative cooling? Radiative cooling occurs because you have a hot body, a cold body, and so it's trying to come to thermal equilibrium. And so, and you need an open system to do that. So the hot body transfers radiative to everything else. This is not. This is not an open system. It's closed, but the power carried by the field is negative. As I say, it's uncomfortable at first. Is there another question? Yes.
Kind of like you have sympathetic cooling when you have like a chain of cut lines and they interact with each other. So via this.
I'd have to think about that. Even this, when I draw this resistor, is an open quantum system. Maybe that's what you're getting at. The resistor is hot and it's getting heat sucked away, so to speak. It's a little uncomfortable. And the sympathetic cooling ultimately also is a non-conservative process, but maybe I shouldn't object. Maybe it is like that, but I have to think of it. It's a good question. He asked if this is like sympathetic cooling. All right, so I'm just going to very briefly talk about the quantum theory of matter waves, not to really introduce quantum theory at all, but to show consistency with things that you might have seen in electromagnetics. So if you have a gauge field classically, then quantum mechanically it's associated with gauge particle, call it a matteron, but matterons are never free. All right. Also in particle theory, there are also particles that are never free. So maybe for those of you who are familiar with that, that's not so bad. But here, the field is stuck to its source. And by the way, also by Roy Glauber, there's this fun article, Amplifiers, Attenuators, and Schrodinger's Cat. This is a fun article because it does something very non-intuitive. It solves the harmonic oscillator problem, which you're familiar with. For example, you were asked about.
Sorry. Is it possible to observe hadrons just in the way that we observe photons?
Pardon me?
Is it possible to observe hadrons?
The answer is you cannot observe them in isolation the way we can observe. The question was, can we observe matterons the way we observe photons? The answer is not in isolation as we do with photons. I can put up a photodetector and I might be getting a photon from the sun, right? But you can indirectly detect their energy here by various experiments to see that they do carry back negative energy, but not directly. They always attach to the atoms. Okay? You're welcome. You can also see them exchanged in principle by mixing waves together. All right. Well, you all know what the harmonic oscillator behaves, and this is a classical one which decays in time. Glauber introduced the inverted oscillator, which is a really weird looking thing, right? If you like non-intuitive, but it's such a nice paper. And whereas this introduces dissipation, energy loss, this thing will have gain. Very interesting, you know? This is the inverted oscillator. The interesting thing is, so go look it up. It's a nice thing to learn about and seems completely useless. But then it turns out someday to be very useful to understand. Here you understand dissipation. Here's a way of understanding how to introduce gain in a quantum mechanical system is with an inverted oscillator. Anyway, the point is here, everything in an inverted oscillator looks the same. These are all the raising and lowering operators and their action. The only difference is that the Hamiltonian now, in the case of an inverted oscillator, has a minus sign out in front. And so negative energies are not unheard of. And so when you get stuck in thinking about the matteron, the fact that it's bound to a particle, the fact that it has negative energy, you can think of the inverted oscillator as being a nice example of a system that has negative energies that are in fact very useful. All right. So quantized matter waves. As I said, a particle cannot be created without creating its gauge field. And that's the difference. So states, operators associated with the particle, along with its gauge field, must have two indices. One is the oscillation frequency, that wall vibration frequency you saw with the superballs, and the other is the energy of the particle. So when we talk about single mode in electromagnetics, we just put a frequency to label that mode in electromagnetics. When we talk about a single mode in matter waves, we just put a single frequency, given its Planck-Einstein frequency, we write it down and we think of a plane wave, for example, a particle as a plane wave. In the case of matterons, excuse me, in the case of our matter waves, a single mode has two indices. One is the oscillation frequency, and the other is the energy of the particle, which has to be greater than the oscillation frequency. And here's a key point, which will not be driven home today. A key point is all the matter waves you associate with the BEC is a Maxwell matter wave at zero frequency. It only has one index, that's omega, right? That's the energy of the particles coming out of your, leaking out of your BEC. And it has no oscillation frequency, or better said, the oscillation frequency is zero. So these Maxwell matter waves are entirely consistent and the same as the de Broglie waves you associate with the BEC, but a BEC is a DC source. Yes.
I could ask a trivia question.
I love any kind of question.
I was curious because you said this relation you don't have the maximum. The maximum is just like speed of group, which is the limit.
Yeah.
My question is, but is the speed of light still max?
Well, the answer is of course, but I didn't write down a relativistic theory. Just as Schrodinger's equation is also not a relativistic theory, so it has its limits, right? And there's a lot of other things that fall apart when I start getting particles to move very fast. For example, their scattering becomes very complicated. All right, so this applies to very slow, very low energy particles. You get them going too violently, much less the speed of light, then things fall apart way before relativity does. Good question. The question was, is there still a maximum? The answer is, of course, a lot of other things happen before that relativity kicks in.
So in both theories, waves, the volume waves, and there's a concept of mass.
Yes. Mass of a photon?
Zero. And in the wavelength, it's a mass of the particle.
That's right.
But would be, is there any sense of speaking about
Yes.
mass?
So the matteron is massless. All right. However, it carries momentum. Like the photon, you can associate a mass with it, associate with a photon. So it carries momentum. It's massless, but it's also bound, and that's the kind of peculiar thing about it.
It is only sending the electric field
To the I'd say it's a lot like the photon, and it's massless. It carries momentum. The difference is it's not radiated, so you never get it in isolation. But otherwise, you can exchange it through multiple particle interactions. They can exchange the matterons. As I said, so far I haven't found the matteron concept so useful, except to answer questions of what's like a photon. But maybe someday they'll be more useful. I had this one and then this one. Go ahead.
So we're using the matteron to describe some kind of underbalance interaction, right?
We're using.
So the matteron is supposed to describe some kind of underbalance interaction.
No, it doesn't. That's, he says, are we using matterons to describe some van der Waals interaction? That was your question, right? Right.
Yeah, because what I'm trying to point out is that it's massless and it should be a long-range force, right?
Yeah, you've got the good theory in you, except it's, so if we were doing relativity, that would be correct. There's no reason it has to be a long-range force and massless. It's not radiated, all right? If it's not radiated, it's not going to go very far, right? And so those two are definitely connected. It's long with electromagnetics, long range, because the photons can be radiated. Here they are bound, so they're never radiated, and they end up short range. Okay?
when we say bound, like again, a trivial question, where exactly are they? With a particle, then the matter moves along with the particle, so photons get like really.
That's right.
They get created basically if you have like an energy level changes, or they are like the messengers. So with the macarons, they are bound to the particles are there.
Right.
It's basically right.
Well, you know, the way I think about it, but this may make things worse or better, depending on who you are, is that this is the way I think about it. The particle, instead of moving like that, classically, and it's really dangerous to try to mix the particle and the wave things together, but instead they're undergoing dipole oscillations and they move along. So think of the Super Bowl, right? They, you know, they essentially remember that they're being vibrated at frequency nu. So it's a flawed picture, but you can think of the things as they move along as being going back and forth. So the matter is interacting or letting the particle know that it's there because it's moving the particle with longitudinal dipole oscillation. It's a dangerous picture, but it's the way I think about it, and sometimes it gives me a convenient way to say that the field is really there. Oh.
It's regarding the behavior of the oscillators. How does it behave in, let's say, dissipation of
This guy? This one, when it falls down in energy, the motion gets larger and larger. So that acts like an amplifier. Pardon me? When you shift from quantum to classical, yes. I'm sorry, it's just the background noise. So ask it again.
So in the case of decoherence, does it shift from quantum to classical?
So the question is, when you have decoherence, does it shift from being quantum to classical? So not necessarily. Whoops. So this is usually described. This ball up here is a coherent state. It is. You know, that's the closest thing to being both classical and quantum mechanical is a coherent state, right? And this coherent state decays in amplitude. Indeed, we have a laser field, right? That's highly excited, and I don't keep pumping it, it'll decay. It'll still be kind of a coherent state as long as the decay isn't too dramatic. And that's kind of this situation. All right? And,
Dana, maybe it helps. I'm not sure if this is going to help, but this is a very unusual oscillator because not only is the potential inverted, but the mass is negative. Okay, so that makes the big difference. That's why it works.
Yes.
Now you can imagine this oscillator as a Bloch field. You know, where you have a lot of magnetic sublevels. And you just look at the very top of it. Then it's exactly the oscillator that Dana is talking about.
And actually, I only use this in this lecture to talk about how it's okay to have things with negative energy, first of all. And if you want to sort of learn more about them generically, go read that paper. It's a very fun paper. Well, I think it's fun anyway. My only point was is that the matter has associated with the negative energy. And so instead of plus h bar omega, it has a minus h bar nu. And that was the next point, I think. There it is. Is that a single mode of this matter wave has two indices, one corresponding to the energy of the particle and one corresponding to the energy of the matteron. And it's the energy of the matteron is subtracted off. And so I was only using the inverted oscillator to say, look, folks, negative energies are, you know, not, if you want to get more comfortable with them, here's some reading to do. This should at first make you comfortable, but this just says in order to not have a negative total energy, omega has to be greater than nu, and that you have a pair to describe a single mode. Electromagnetics is only one parameter. a plane wave atom has only one parameter. Single mode of this has the two parameters having to do with the atom and the field. All right, so single mode has somewhat different language. And there's also something equivalent to noise in the vacuum fluctuations in the system. But as I said, this isn't really a talk about quantum. I'm almost done here for this lecture. Yes?
On that slide, I see the brown phone still have a negative energy if we go back.
Yeah, so if you have none, do you still have the minus HR omega? And the answer is yes. And that would mean that that there's some fluctuations associated, but you can't have nothing, right? You can't. You got that right.
So it's like nothing. Saying, oh, well, it's negative energy doesn't make sense.
But you need some mass, a BEC around, for example, that is in its ground state, is a DC, and then that will be subject to fluctuations. Okay? All right. So, de Broglie said matter is classically a particle. And the particle phenomena, wave characteristics are revealed by quantum mechanics. Coherent matter waves corresponds to an oscillating current of particles, for example, along with their gauge fields, are described by a set of Maxwell's equations, just like light waves. And coherent matter waves, we can really think of them, forget about the quantum picture, go back to Maxwell's picture. Now we have, again, matter classically given by a wave description, not a particle description, classically. So it's the complement of de Broglie's picture. If we had somehow come across matter waves, this kind of matter waves, first, we've said, oh, it's a wave, and then we would have discovered there's particle behavior underneath it, just like we did with light. That's not the way we were brought up, but nevertheless gives you a different picture than you've had before. All right, so far, field theory of matter waves. An oscillating flux of ultra-cold atoms is associated with a gauge field whose physics is described by matter wave analog, I should say dual, to Maxwell's equations. These waves are associated with a minimum rather than a maximum velocity. And, as I say, it's really a limiting velocity. It goes a little deeper than just saying, oh, it's a minimum like the speed of light is a maximum. The field did not propagate in source-free regions like photons, electromagnetic field does. They're associated with negative real-valued impedance. They carry negative power from their source, meaning they provide cooling. The quantum picture, matteron is the matter wave analog of the photon. Each matteron is bound to one particle, and a matteron is associated with negative energy, and the total particle from the matteron field is always positive. And the coherent matter wave state is an analog to the optical coherent state. And single mode excitations of a matter wave field involve both the frequency of oscillation and the Planck-Einstein frequency corresponding to the particle energy. So we write down a set of Maxwell's equations that look like Maxwell's equations, but I changed the letters. So this is meant to go along with the matter field. There is a particle group velocity, which is dispersive, unlike the speed of light, and there's the quantum impedance replaces 377 ohms. You can combine the Maxwell's equations to get wave equations for these fields sourced by the current and charge density. Here, the current being particles per second per unit area, or mass per second per unit area. Likewise, for the charge density, you source the electric field analog or the magnetic field analog. And these equations are wholly consistent with quantum mechanics. Their solutions describe quantum mechanical pure states in the same way that a coherent state electromagnetic field is the pure state of the quantum state. So are these states pure quantum mechanical states. And most importantly, and what's new for you, is that these waves have a global temporal coherence. And you can consider these solutions AC matter waves, whereas the familiar de Broglie waves, something that the atoms that you get from a BEC are DC versions of this more general kind of wave. So we'll go over their properties next time, and this leaves plenty of time for discussion. And I did sort of, we'll run through the actual derivation of going to Maxwell's equations, starting from the Lagrangian. As I said, we took this from this, more or less, from this nice text by Wheeler. It's written very, very clearly. Unfortunately, probably my guess is he passed away before it was done, because there's chapter 1, chapter 3, chapter 5, chapter 2, but no, bunch of missing chapters, but enough so that you can figure out what he wanted to do with field theory. Yes.
In which this approach would be more preferable than regular approach electromagnetic field theory.
Then electromagnetics. I thought you were going to say quantum mechanics. So
they should describe the same phenomena, and this is but what are the problems that potentially easier to solve?
well, so the question is, you showed electromagnetic theory, showed matter wave theory. The only reason I show electromagnetic theories is because I assume that most people are familiar with it, and it's just a baseline. We'll see when we apply matter wave field theory, classical matter wave theory to solving problems, that we get answers that are very different from the quantum mechanics, and sometimes look more electromagnetic, and sometimes we'll get differences from the electromagnetic that look a bit more like you'd expect for quantum. But in general, you'll find there's a whole new set of physical phenomena that we didn't really have a context to think about, such as a Fabry-Perot cavity for matter waves that play the same role and take advantage of temporal coherence in the same way that electromagnetics. Nevertheless, because the atoms have mass, these cavities act rather differently than their electromagnetic counterparts. I hope it will become more clear at lecture number 2.
So in quantum mechanics, usually we like to have a ground state, right? Mean value found
That's a very good question. In reality, even in Glauber's ideal system, so the question was, where is 0? Where is the ground state? Ground state in Glauber's inverted oscillators at the top, right? And you go negative from there. Therefore, something eventually becomes wrong with it, because we can't have negative energies forever. But nevertheless, we can learn a lot about the construction. In our case, I was merely using Glauber to show that actually there's nothing wrong with our negative energy. It's bothersome that a particle has negative energy, but things work out such that you always end up being positive. And the ground state of a system, it depends on, for right now, it's your philosophical preference. The ground state could be what we consider vacuum, in which has no mass. And then this theory doesn't make really any sense. You can't get going. You can't create mass, right? So for us, the vacuum state would actually be a condensate with particles associated with particular frequencies. So I've got no matter on energy in there, just the mass. That's DC, and that's the way I'd consider the ground state. It is not the vacuum state, but it is a ground state.
Is it surprising that you get the same equations in the same form when you do the relativistic versus the quantum treatment of this?
Well, yours truly, when I first doing it, says, "Oh, that's cool. I didn't know that." The answer is that if you read work, he says, "Oh, you get a family of these Maxwell's equations. This is what you get, right?" And then you have to go through these extra exercises like, "Oh, what's the equivalent to the speed of light?" But but yes, it's a family, and then you identify the member of the family by tying down those parameters. And to me, that was news. And when you read, but if you read about gauge field theory, you'll never realize that from modern treatments, because they always immediately invoke just one, because they immediately evoke relativity.
You showed that the Maxwell macro wave kind of a generalization of the Roy macro wave when the second parameter is equal, no?
Yes.
So this means that these are like, does it mean that the macro macro is a generalization of it, or are they two fundamentally different macro waves that can be looked at?
Let me correct your earlier statement just a bit, amend it. You said a de Broglie wave. I've used that term very closely when I've said BEC, because a BEC produces a coherent state of many atoms, right? Whereas a de Broglie wave all by itself, we can associate with a single identified particle. And so the BEC is the particular, say, DC member of this larger set. The de Broglie wave, there's, roughly speaking, there's quantum mechanics of massive particles over here. Over here, we have quantum mechanics of the electromagnetic field, and they're rather hard to put together. You can, but it's not trivial to put them together. Here, we still have the de Broglie quantum mechanics of a single particle, but then when we go into those coherent states, start with the BEC, and then it's easy. To make them bridge, you can do it, but it's unpleasant. Another way is try to write down the wave function of a photon. You can do it, right? But it's actually not as trivial as you might hope when you first come across it. You had a question?
Yes, I'm not sure I understood fully in the beginning. You said we cannot use Bose-Einstein condensates as those matter waves in the public world cavities, so they bounce like that, because their coherence is not temporal or global.
So,
but then when you use this kind of picture to describe matter, and you just wonder Wells forces, which is, I guess this is also in Bose-Einstein condensates that scattering
exists, and you get mean fields and blah, blah, blah. So first,
find some other state of matter that can be coherent for a longer time, but it's not Bose-Einstein.
So a BEC, if I have a nice ideal experiment, is coherent. It has quantum mechanical coherence, right? So no questions there. But it is not temporally coherent. And that means that as it goes, that there's no, here's another way of thinking. There's nothing to measure in a BEC really except for the flux. There's no field that you can measure its strength as it's coming out. E and B, electromagnetic fields, are independent. You can measure with a meter the electric field and magnetic field. Likewise, in these coherent matter waves, there's a field which in principle you can measure with, measure classically of this electric field analog and magnetic field analog. So that's key number one. And then there's the temporal coherence. That's what allows me to think about resonators rather than traps. A trap, I think, is I can solve for some quantum mechanical ground state of that trap. Or I could solve for the matter wave modes, Maxwell matter wave modes. And those are two quite different things, as you'll see in the next lecture. The answers you get are completely different. Say again? So you combine Maxwell's equations, then you get a second order wave equations, right? So they are second order, yes. Yes, second order. Yes.
So isn't that weird? Showing the equation that is
Yeah, I mean, it is weird. It's not Schrodinger's equation. On the other hand, Maxwell's equations, remember, the solutions are quantum mechanical pure states. Even though I didn't do anything with Schrodinger in the same sense, all is okay with respect to quantum mechanics. It's just not Schrodinger solutions. They're not wave functions. They are states of the system. You can, as I said, it's miserable. I know like Wolfgang would agree with me or not, but they involve these Glauber P functions and quasi-probability distribution functions and things like that. But you can, but it's not simple. No apologies. You've been the best question asker so far.
The very main question. So this invariant oscillator is describing matter waves, right?
No, it's not. I'm sorry if I communicated that. It's not describing matter waves.
The matter from the matter wave interaction.
The only thing that I used it for is to take Glauber's treatment to talk about negative energies, and I could go further in a coherent state in an inverted oscillator. And it is true, in the highly excited matter wave state, it is a coherent state with negative energy associated with the field. And in that sense, it's very nice with Glauber. Part where it breaks apart from Glauber is that you also have the particle there, always ending up giving you a positive energy. So it doesn't have this issue of infinite negative energies finally. Okay. Okay. Well, your time's up. My time is still here. Thank you very much. And next time I'll go over the properties of these matter waves. Oh, this is mine. You're welcome. Oh, I love it. No, not I like talking. I won't remember that.
But maybe alphabet basics. It's always negative on voltage oscillator and the energy. And it was not the how to say it? I mean, not the parallel to each other.